Hey, welcome back everyone. Another Ask Mark session here at Blue Glow Electronics. Most of our Ask Mark questions and answers are fairly simplistic in nature. This one's a little more in-depth, so you may actually learn something here. First up, an email here from Tim Burcham. He says, Mark, love your videos. I'm a novice engineer getting into restoring radios. I purchased a beautiful Grundig 4570 a week ago with the right channel not working. He basically says he's traced the problem to a disintegrated output transformer. See the photo, and the right channel, basically output lead from the ELL80 output tube to the transformer, was disconnected. From the attached schematic, can you help me determine if this is a single-ended transformer or a push-pull type transformer? How would I determine the correct transformer to use as a replacement? By the way, I sent this question to the folks at Hammond, the transformer manufacturer, and they could not give me an answer. So anyway, Tim, I'm going to try to give you your answer today. Okay, before we get into answering Tim's question, we're going to break this video up into two segments. First, I'm going to answer Tim's question about it being single-ended or push-pull output transformer. Then, I'm basically going to go into some depth about output transformers, and I think this will be an excellent class today, so stay tuned if you want to be a student. Okay, we're going to pull up the schematic here, and Tim was kind enough to provide one. I did take the output section and blow it up here just so we can zoom in on it, because it's really all we need to be able to figure out Tim's couple of questions here. His first question was, is this a single-ended output transformer or is this a push-pull output transformer? Well, we're lucky enough to have a schematic. If this wasn't, and it was just a transformer laying loose you found at a yard sale or something, then we got a different scenario, and maybe I'll make a video on that one day. But this, we have the circuit, which helps us a lot in identifying the transformer. So pretty simple. Let's start talking about known facts that we know, okay? This is the speaker, and we know that this is the right channel, and we know this is the left channel. It tells you right here, right channel. We know that this speaker is being fed by this output transformer, and we know this speaker is being fed by this output transformer, okay? We're just walking up the line. We know this output transformer is being fed by this tube. And we notice that this output transformer, if you notice the plate coming off here, feeding into this output transformer is being fed by this tube. Okay, so to have a push-pull configuration, guess what you must have driving an output transformer? 2 or more tubes, okay? So we can deduce from just the fact we have a single output tube here driving the output transformer that this is a single-ended transformer right here and not a push-pull. Now, we can dive in a little deeper and if we wanted to into the actual transformer, which I think is worth us doing. And I'm going to redraw this transformer right here because it's a little funky. Everything Philips does with their schematics are a little funky. If you notice these little resistors here, that's not a very common way of drawing these resistors. At any rate, we're going to draw the two sides of the transformer as ugly as I can here on camera. And we know this is feeding the loudspeaker, and we know this is feeding over here, but we've got 3 wires here coming out of this. So we know one of them is a tap somewhere in the middle or potentially off of the middle of this. So we've got 3 wires coming out of this transformer. Here we got a green wire, black wire. We know that's easy. On this one, we've got a blue up here on one end, a red, and a yellow. Well, the blue is coming off of the plate here, which is typically all the way at one end of the transformer. However, the other side of this, there's 2 wires here, and let's take a look at this wire right here that comes down. It's yellow. It feeds down through a resistor, same off the other one. They tie together. Where do they go? They come over here and they feed into the screen. So all you'd have to do is pull up a picture of this EL88, pull up a data sheet for it, and you would see that this pin right here is the grid, right? The screen. So tied here to the screen, coming off over here, tied to the screen, we now know that this yellow wire is the screen tap. So we can put it right here. It's somewhere in the middle between the 2 ends of this transformer. Next up, we got the red wire coming off. Where does the red wire feed? It feeds down, ties in with the other red wire, comes down here, ties into what is part of a filter capacitor here, and it's also tied over here, comes around into our full wave rectifier right here. And as you can see, so we're feeding here with B plus down this line, coming up. It's being filtered some by this electrolytic capacitor. It's being fed up. It's fed into this output transformer. It's being fed up. It's fed into this output transformer. So we know that the red wire is at the other end of the winding. So this represents the length of the windings inside the transformer. Red's on one end, blue's on the other. Yellow is somewhere in the middle. We know that because it is a screen tap, and screen taps are somewhere in between these two. Now, a push-pull transformer has 3 taps on it typically, okay? Except for in a push-pull configuration, this red wire would go to the plate of one tube, this blue wire would go to the plate of the other tube in the output push-pull configuration, and the B plus would be fed in via the middle wire. It's not the scenario we've got going on here, okay? Oh yeah, by the way, while I've got it, this little device right here, you may wonder, what the heck is that? Well, that's nothing more than a jack, an output jack that you could use, same here. You could use these to bypass the speaker. That's what this little push here is. And these jacks are on the back of the unit. So in other words, you could plug in an external speaker and bypass the internal speakers, okay? One more known fact we're going to notice while we're here looking at this schematic is this is a 5 ohm speaker. So we've got a known quantity right here. All right, now we've answered the question, is it single-ended or push-pull? Let's now go out and figure out how. Oh yeah, by the way, we know this fact. Okay, let's talk about our known facts. If you guys remember back in science class or math class, if you're trying to solve an equation, the first thing you want to know are the constants or things that you know. We know that the output secondary is 5 ohms because that was on the schematic, okay? We also know from textbooks on transformers that the windings ratio is directly proportional to the voltage ratio. And today, for what we're doing, what we really need to work with is this voltage ratio, and I'll show you why in a minute. And that is equal to the voltage on the primary divided by the voltage on the secondary. In other words, it's the ratio between these two, okay? Then we know from the textbook also that the impedance ratio, and that's what we're really chasing today, is going to equal to VR squared. In other words, the voltage ratio squared. And one last little known fact here I'll leave you with is Uncle Doug made a very good video on this topic. If you'll search for it, I'm sure if you type in Uncle Doug transformer, it'll come up. It's a great video. Okay, before we can truly help Tim figure out which type of transformer he needs, we need to learn a little bit about output transformers themselves. And so hang tight. This might be a 5 or 10 minute lesson, but I think it'll be worth it and help make sense of a lot of this. Okay, what a transformer is, an output transformer, is it's nothing more than a coil of wire and another coil of wire over here, okay? And these two coils of wire are not connected to each other electrically. That is very important, okay? I drew these two little lines here. This represents the iron core in a transformer. We'll talk more about that in a minute. But imagine this is a coil of wire and this is a coil of wire, okay? And what happens is we feed an AC signal into this coil here, okay? And what happens is it induces a AC signal in this coil that feeds back out through its connections purely through magnetic flux, okay? And so what happens is the closer you get these coils to each other, the easier it is for it to induce this voltage across. And if you wrap these coils kind of up through the middle and through the middle here and then in between them with an iron core, the permeability of that iron core keeps this magnetic flux kind of tightened in, and it helps with that transfer from one coil to the other in the most efficient and effective way possible, okay? And so at the end of the day, what we're doing in a amplifier is on this side, we have the power tube, right? That's doing the amplification. You take in little bitty signal in your amplifier. Along here, it turns into a great big signal. This great big signal has two things. It has high voltage, okay, associated with it. Typically anywhere it's equal to the plate voltage plus or minus the swing here of this signal in the middle. So it could be as much as 300, 400, 500, 600 volts we're dealing with here on this side. Also, the power tube here has an extremely high internal impedance to it. Okay, so it's looking for a load that has a high impedance to maximize the power transfer from this tube into this coil here. Okay, so what we're wanting to do here is have a high impedance, which we denote with high Z here. Okay, and what we want to do is transfer this AC signal out the other side, and we're wanting to kind of transduce it back into a smaller signal, okay, smaller voltage over here. So if let's just make this up, we had 400 volts going in on this side. Out on this side, we might want to get out 20 volts or so. Well, here's the good news. When you induce an AC signal into this side, the number of windings in this coil and the number of windings in this coil matter, okay? So if you fed in a 10 volt signal here, and let's say you had 10 windings, and on this side, you had 100 windings, okay? In would come a 10 volt signal into this 10. The ratio of windings, 10 to 100 here, all of a sudden on this side, you're going to get out 100 volts on this side because you've got a 10 times multiplier in your windings ratio here, okay? Which is directly proportional to the voltage ratio here. 10 volts in, 10 windings, or it could be 10 volts in, 100 windings, and then over here it could be 1,000 windings. Either way, it's a 10 to 1 ratio. You're going to get 10 times. So out, instead of 10 volts, comes 100 volts on this side. Well, the inverse happens with current. If you were feeding in 10 amps of current here, that 10 to 1 ratio there, this side gets out 10 times less current. So out this side, what you would end up with, instead of 10 amps that you fed in here, you would get 1 amp, okay? So a 10x multiplier in voltage, a 10 times divider in current here on this side. So what we're going to gain here is high voltage, high impedance, low current here, right? Out this side, what we're going to end up with is low voltage, we're going to end up with low impedance, and we're going to end up with high current here on this side. That is the purpose of an output transformer. You say, well, why do I need that? Why wouldn't I just connect my speakers up right here? Well, first off, speaker coil impedance, the winding in the coil, it's not. So a typical tube output might be looking for 3,000 ohms of impedance, okay, that it's wanting to see to effectively transfer. Well, speaker output won't be 3,000. It's typically what, 4, 8, 16 ohms, right? So you need something to transfer that over. Second off, you connect your speaker leads over here and you put 400 volts on them, right? And somebody comes along and they're like, oh, the speaker lead's loose on the back of the speaker. Let me tighten it up a little bit. You just introduced an external 400 volts to your amplifier out here on these wires going across the room that your two-year-old toddler might walk up and pull out of the back of your speakers. Next thing you know, your 2-year-old toddler got zapped with 400 volts. It's a bad thing. So we want to play with low voltage. We need this low impedance because that's what speakers are. And we need the high current to drive these speakers effectively. So that's what this output transformer does at the end of the day, is it transduces all of these things from one side to the other. All right, if you've got that, hang tight. I'm going to raise the level of the lesson up just a tad bit more, and we'll get to the next step then. This is probably the most mysterious part that people really struggle to get their heads around, and so I'm going to try to take my time and break it down for you simply here. When you go to a website like Hammond or Edcore, or you name the output transformer, and you look up and you find the specs on a transformer, and let's say it says it has an 8 ohm primary, and it has, has an 8 ohm secondary. Its primary is, let's just say, 3,000 ohms, okay? This unit can handle 10 watts of power. It's how much it can transfer from here to here without this transformer overheating and losing efficiency and having problems, okay? So that's measured in watts. And then there might be one other little spec that shows up, and it's called DC resistance. Keep in mind, everything we're talking about is AC, feeding an AC signal in, getting an AC signal out. Well, if you hook up a DC multimeter digital multimeter here, and measure from here to here, there will be the winding resistance from a DC standpoint from one side to the other. And I'll just make this up. Maybe it's 150 ohms. That does come into play sometimes. Some transformer manufacturers give you the DC resistance of the windings. Some of them don't advertise it so easily. So I'll talk to you a little later about where that might come into play at, okay? It's a little irrelevant to what I'm talking about right now. But let's go back over here to, we've got our input, we've got our output or our primary, our secondary, got this iron core in the middle. If you found a transformer that had 8 ohms on the secondary and 3,000 ohms on the primary, I need you to understand there is nothing about this transformer that is 8 ohms or 3,000 ohms. It is purely a representation of, if you feed, okay, an 8 ohm load on this side from an AC standpoint, this side will see that interpreted, because of the windings ratio and the impedance ratio here, it will see it interpreted as 3,000. There's nothing you can do, there's no meter you can hook up to either side and measure and get 8 ohms or 3,000 ohms. So in reality, there's a ratio here. If we did the math and divided this out, so in reality, if I had my choice, the way transformer manufacturers would list their transformers for sale would not be this, and we did the math here, 3,000 divided by 8 equals 375. That is our impedance ratio, 375 to 1. Okay, for every 375 ohms of impedance over here seen, let's just say the load is here, it might be better said this way, for every 1 ohm of impedance seen over here, this side will see 375 ohms. It's all about this reflected impedance as a result of this transfer and kind of the internal, for lack of a better word, I'm hesitant to use the word reactance here because we haven't talked about that, but it is the hindrance that this sees, the amount of impedance based upon a 1 ohm. If this bumps up to an 8 ohm speaker, you multiply that, it sees 3,000 ohms over here. So if I had my choice, transformer manufacturers would not do this. Instead, they would say the impedance ratio of this transformer is 375 to 1. Its power handling capabilities is 10 watts, okay? It might even talk about the bandwidth of this transformer. This transformer is good from 10 hertz to 30 kilohertz. That, and then maybe the DCR, okay, the DC resistance of the primary here. That's what I'd like to see transformer manufacturers stamp on their transformers. And they used to find a lot of military transformers with this kind of stuff on them, okay? Things have gotten simple. When people were working on equipment, they knew this impedance, they knew the speaker impedance, right? They could look up in a tube manual what this power tube is looking for, and it made it easier to go label our tubes, our transformers this way instead of this way. This way, it's independent. Hey, if I wanted to run this with a 4 ohm load over here, it's 1,500 ohms over here. And you can do that. You can take a transfer that's labeled this and stick it on a 4 ohm load and get a 1,500 ohm impedance on the other side of it. So don't get wrapped around these are specs for the transformer. They're more another way of showing, using common known loads, this impedance ratio that I would rather see them labeled with. I hope this makes sense. If not, ask questions down below. We will try to answer this. It is the mystery that needs to go away. Here we are back with our sheet. Here's the specs that we need to go look up for Tim, okay? We know this one, 5 ohms, okay? We don't know what the primary is here, right? We don't know what the screen tap is. We don't know the wattage here, okay? And we certainly don't know the DC resistance here of this. But what we do know, okay? We know the blue wire and the red wire are the furthest apart from each other here because we've studied the schematic a little bit. You could also use an ohm meter to figure that out. You will have more resistance from the blue wire to the red wire than you do from the blue wire to the yellow wire or the yellow wire to the red wire, okay? What you cannot do is use the ratio of resistance here, okay, to try to figure out your screen tap percentage. We'll talk more about that in a second. We do know that the green wire and the black wire here are connected. All right. If I were you, Tim, before I went any further on this journey, I would get out my plain old multimeter of some sort here. Something along this lines. I would put it on resistance and maybe turn on the continuity beeper. And I would measure between here and here. Make sure you've got resistance there. If you have zero resistance, it means you have an open transformer. It's bad, okay? Let's say you find some resistance here on this side. Then connect from blue to red here. Okay, see if you got resistance. If so, then see if you got resistance between blue and yellow. Then make sure you got resistance between yellow and red here, okay? If so, it's possible you've got some shorted leads in here, some windings in here that are shorted and you're seeing less resistance than you should. Thus, this transformer is not working effectively. It's possible, but in more likelihood, this is a good transformer. You need to solve something else in your radio, not the output transformer. But if any of these are open, you definitely have a bad transformer at this point. So once you get that out of the way, next, I would move here to the data sheet for this ELL80 tube, okay? Let's look up here. This is in German, so there's a lot of it I can't read, but there's some parts of it here I can. This says typical operation. This says Class A amplifier, which is what? The same as a single-ended amplifier. Then I scroll down through these values. Voltage, ohms, milliamps, kiloohms, voltage, percentage, W. That's wattage. What do we got here? 3 watts. I don't know what this N stands for because I can't read German, but basically this is telling me that this tube's plate dissipation is 3 watts. So this tube won't put out any more than 3 watts, okay? So if I were you, I would look for something like a 3 watt to 5 watt transformer. Could you get a 10 watt transformer? Yes, it goes from being this big to this big. Could you put a 20 or 30 watt transformer? Yes, it starts to get bigger. You got to figure out what'll fit in your radio. But we're going to come over here and we're just going to put 3 to 5 watt output transformer that we need right here. So we're starting to fill in the blanks here, starting to answer some of these unknowns that we don't know, okay? Up next, I want you to get 2 devices, okay, you're going to need to do this test with. You're going to need some type of signal generator or function generator, audio signal generator, something that operates in the audio frequency, something between 1 hertz or 10 hertz, somewhere in that range, up to about 20 kilohertz is what you're going to want here, okay, the generator. If you find an RF generator, it won't work. That's way up in the megahertz range. You need a signal generator. You're going to connect it on the output here. Why are you connecting it on the output? Because we already know this impedance right here on this side. This is kind of our known side. The next thing you're going to get, either a digital multimeter, analog multimeter, or an oscilloscope. And you're going to connect it across these same leads. What you're going to do is you're going to feed a signal in on this side, kind of backwards from normal. So we're going to kind of reverse induce this signal through this transformer here, okay? And we're going to do something like, and I'll just make this up, a 10 volt AC signal into it. And we want to pick something here in the audio range because we know this transformer transduces the audio signal range well. So for kicks and giggles, we're just going to use a 1 kilohertz signal. It's a good signal that will feed through this transformer quite easily. So we're going to feed 10 volts in. And what we're going to do then, once we make sure that this is on 10 volts AC going in, if you have 2 digital multimeters, hook the next one up over here, or 2 oscilloscopes. If you got an oscilloscope with a second channel, put the second channel over here. Connect one side to the blue, the other side to the red, in other words ground, and then the tip probe here. If for whatever reason you don't have 2 meters, just move this one over here once you know this has got 10 volts AC coming out and measure what you get out on the other side. It's going to be something much larger because there's more windings on this side. Remember in our picture earlier, we talked about going from 400 volts down to 10 or 20 or something. Well, if you feed it the opposite way, you're going to go from 10 or 20 up to 400 or so over here. Measure your output on this side over here. For kicks and giggles, to make the math easy, I'm just going to say we get out 100 volts on this side. So we can then take, and remember our voltage ratio we talked about earlier, it was one of our constants up here, is equal to V on the primary, 100, divided by V here on the secondary, fed in 10, right? Our voltage ratio is 10, or 10 to 1. For every 100 volts we feed in over here, we get 10 volts out over here. For every 10 volts we feed in over here, we get 100 out over here. If it was 40 volts in here, 400 out over here, 500 in over here, it's 50 out over here. It's a 10 to 1 ratio, okay? We're not going to get into the turns windings today. That's not all so important. But what we do need to know is the impedance ratio of this transformer is equal to, remember, we talked about it earlier. It was the voltage ratio squared. Well, if you say 10 squared, and if you do both sides of it, 1 squared, well, 10 squared is 100, and no matter what you do with 1 squared, it's still 1. So your impedance ratio is equal to, there you go, 100 to 1. So let's just say we got the 100 volts out here. We did the math. We know our impedance ratio is 100 to 1. It's probably not going to be 10 when you do yours. It's probably going to be something like 350 to 1, right? But then you know, hey, we've got a 5 ohm here. 5 times 100, 500 ohms of impedance on this side is what this transformer reflects back, okay? Remember, that's the impedance. That's when the load looks in here, but there's a 5 ohm load on that side. What does it feel reflected back? It feels this 500 ohm. Guess what? Tim, you're going to need a 500 ohm. It's probably not the case in yours. You need to do the math. You need, if this transformer is good, measure it. If it's not, unconnect the wires from the right, if the right channel is the bad one, unconnect the wires from the left channel transformer. Do all these measurements using the left channel transformer. It'll help you figure this out over here. Okay, now, next. Is everybody clear on that? All right, next, we're going to go one more step deeper into this, down this rabbit hole of knowledge here. We got to figure out the screen tap. Well, let me tell you how we're going to do that. We're going to come back over here to the signal generator on this side, and you can disconnect this. I don't care what voltage you're feeding in. You just want to make sure you're reading AC voltage on this side. Feed a signal in on this side until you get something out on this side that is a multiple of 10. 10 volts out, that works. 100 volts out, that works. 1,000 volts out, that works. Okay? Just make sure, irregardless of what you feed here, you want to get a nice even number you can do some math with on this side. You wonder, well, why would you want that? And why do you not care about this? Well, if I feed something in here and I get 100 volts out on this side, if I then move my little lead here off of this, and I move it right here, okay, and I measure, and let's say instead of 100 volts, I'm getting 35 volts here between the red and the yellow. I disconnect this one and reconnect this one, and I measure between here and here. I better get 65 volts out. Those two numbers better add up to be 100, in other words. But guess what? This voltage in relation to this, I just figured out that I need a 35% screen tap, because this voltage is 35% of the whole, and it'll be the lower percentage, the one below 50%, that'll dictate your screen tap over here, okay? In other words, you're feeding in a voltage into this, and somewhere along the way you're wanting to take a percentage of that back out and feed it into your screen, and that's how it would get measured. Then all we need to know is the DC resistance here. Well, that's pretty easy, okay? Disconnect this again, connect up here, put this on DC resistance, right? Measure from here to here. You'll get your, whatever it is, and I'll just make this up, 120 ohms out. You almost have what you need to go buy a transformer. All right, Tim, you think you're there, right? You now know you need a transformer with a 500 ohm impedance primary. You need a 5 ohm impedance secondary. You need a 35% screen tap. You need it 3 to 5 watts. And if you can find a transformer that lists the DCR, it'd be nice to know that it's somewhere around 120 ohms on the primary, okay? Let me show you why that's important. Okay, if you follow the B+, the positive plate voltage here from the rectifier, right, through, around, using a filter capacitor here, okay? So we're feeding up then, right? And we get to right here. We feed in red on this side of the transformer, and we feed out through the blue. Same here, we feed in through the red, out through the blue here. So let me just draw the path here, maybe a highlighter here. Okay, we're going to come down, we're going to come across, we're going to come here, it's going to come over, it's going to go into the red here, it's going to come out of the blue, and it's going to go to the plate of this transformer. Same voltage is going to come up, come in here, out of here, to the plate of this transformer. What is missing? Well, if you said, hey, where's the plate load resistor? I don't see a resistor in that line anywhere. And you need one. Well, guess what plays the role of the plate load resistor? If you said the windings inside of this transformer right here from a DC standpoint, not AC, DC, you would be correct. So the resistance here of the windings, otherwise known as DCR or DC resistance. So that's where you pick up your plate load resistor, is the actual windings inside. Keep in mind, this device is now playing an AC purpose and a DC purpose for the plate load resistor here. And so you want to try to match that up as close as possible to what's there already. So it's easy to do. You grab a multimeter with nothing hooked up to this and measure between the red and the blue wire. That is your DCR of a good known transformer, okay? Then when you go to buy a replacement, try to match it up. Now, if you can't, okay, and it's going to be off, 20 ohms, 100 ohms, 200 ohms, whatever, and you don't have any other choice, you may have to rebias this circuit here as a whole to account for that, okay? And I'm not going to get into that in today's video. It's a little outside the scope of this, but you could do the same on the other one. And by the way, if that's the case, I would replace both transformers so everything is matched and equal at that point, and you can make this unit work again. So Tim, to wrap up the last piece of this puzzle, here's where your problem's going to lie. You're going to go try to find this transformer, and 5 ohms is not a common value for output transformer. I'm not saying you can't find one. It's possible that some guitar amplifier or something, is a single-ended and uses a 5 ohm speaker, and because it's common enough, somebody's made a replacement transformer for it. But highly likely you're not going to find that. What you're going to end up finding is a 4 ohm output transformer, because that's a common value, okay? Here's the problem. If you put it in, let's say you matched all the specs except for 4 ohms right here, and you put 4 ohms in that place, then you went and bought this and put it in. Well, think about it. When you reflect back from the load through the transformer, right? You got the windings, back out to the other side, and you've got your tube here, right? If you'll remember, if it sees a 4 ohm load, and let's say this up here was 500, you still kept the primary at 500. Well, what's the ratio here? 4 to 500 is a ratio of 125. In other words, your IR equals 125 or 125 to 1 if you want to write it that way. All right, and then what are you going to do? You're going to hook up a 5 ohm speaker to it. That's not going to play out well for you, because when it reflects back through 5 times 125, your tube's going to see 625 ohms here instead of this 500 that it's looking for because of its reflected impedance. So what we really need to do here is figure out what value of transformer that if we put a 5 ohm load on it over here would reflect back a 500 ohm load on the other side, but yet that is labeled as 4 ohms. Well, if we're going to go 5 here to 500 over here, right, that's a 100 to 1 ratio. And if we're going to put in a 4 ohm load on it, let's do the math here with a 100. We're going to end up with a 400 ohm primary is what you're going to want. So that way when you drop a 5 ohm load on it times 100, you end up with the 500 that you originally wanted on this side. So you would not buy a 5 ohm here, you would buy a 4 ohm here, and you would not buy a 500 ohm primary here, you would buy a 400 ohm primary. But when you put it in a circuit with a 5 ohm load on it, That 5 is going to use the impedance ratio here of 100. It's going to multiply. It's going to give you out the 500 ohm load on the other side that you were actually looking for to begin with. And you're going to want the 35% screen tap, the 3 to 5 watts. And if you can match up the DCR as close as possible, do that as well. That's how you go about finding a replacement transformer for your unit. And that's how you go about using using a standard load transformer in place of where you might not have a standard load on this unit. This same trick can be used. Let's say you've got an amplifier and all you have is an 8 ohm speaker, an 8 ohm secondary, and say maybe a 2000 ohm primary. But what you really want is a 4000 ohm primary, right? Well, you could change that around and use a 16 ohm speaker and end up with this output transformer having your 4000 ohm load on the other side. It's all about ratios and what you're trying to get out of it. Hope this made sense to you guys. If not, ask some questions below. I can try to make some follow-up videos, but thought I'd try to demystify this a little bit for you today. And thanks for watching so much, everyone. Have a great day.